So in the previous part, we introduced the material derivative or the total derivative, and we drove a formula for the flow-through acceleration. So the total derivative dv by dt has two terms. It's partial v by partial t, in addition to v dot nabla v, right? That's what we got. And if we break it down, it should give me partial v by partial t plus u partial v by partial x plus v partial v by partial y plus w partial v by partial z. And we did define two types of acceleration. We have local acceleration, and we have the convective or advective, call it whatever we want. Later on, we'll talk about these two terms, acceleration. Okay, so now there is a very famous terminology we use in flow. It's called the steady and uniform flow, steady flow and uniform flow. So I would like to explain each one of these terms so we can distinguish the impact of stating one of these two conditions in a flow on the acceleration part. So let's assume that we have a flow in a conversion section like this. So the pipe section start with a constant diameter part. I'm going to call that part 1. And then the diameter is shrinking down. So I have a conversion section here. That's section 2. Now, and I'm pushing inside a constant mass flow rate. So the mass flow is not going to change. And let's look to the variation of velocity within that section here. I'm going to start with indicating specific locations. So I will mark a location here, Let's actually do the center line of that pipe. So I'm going to mark specific locations, and I'm going to connect a velocity meter for each one of these locations, and keep observing the velocity reading at each one of these locations. So what's going to happen, there will be a fluid particle here. It's going to start going through that location. As soon as it's in that window, the dial will read my velocity, then this particle will continue to move on, right? And in the same situation, I have a fluid particle here. As soon as it's getting into that window, it's going to leave, right? And the same situation here, a fluid particle is going to go through this one and leave. Then a next particle will come and go on. So I'm fixing the position. So this reading here, these dials are at fixed location. And what I do, I collect the velocity reading at different time. So location is fixed, but collect data at different time. So say every 5 seconds, I'm looking into that reading. So the position of that velocity meter is not changing, but I'm counting or collecting data for variable time. What's your expectation for this reading? So if you are pushing certain value of mass flow rate, and the diameter at that section, or diameter at that section, or diameter at that section is not changing, right? So I'm expecting the velocity would be fixed. It's not going to change. So whatever that, the first particle comes in, the second one comes in, the third one comes in. So we are expecting to see that velocity is not changing with time. When the velocity is not changing with time, that fluid called steady, or that flow is called steady flow. So the word steady means that there is no variation of the velocity relative to the time at given location. In this situation, I can translate that partial V relative to the time is equal 0. So for steady flow, the local acceleration equals 0. So that's the first type of a flow. Okay, now let's assume that I fix it. I'm still in the steady flow, right? I fixed the location of the reading of the velocity meter somewhere in here. And I'm looking for one particle to come in and leave. So I'm going to read a specific velocity. Then the next particle will come in, I will read specific velocity. The velocity is not going to change as well. The velocity here is different than the velocity here or here or here because of the difference in the cross-section, flow cross-section. But again, I'm fixing the location. I'm just recording the variation of velocity relative to the time. So the velocity here, yes, for sure, it's different than any velocity here. But this specific velocity for a given particle at that given location will not change as a function of time. So even I have a different flow area, I have a different magnitude of the velocity, but every particle going through that window will always read the same velocity. So still steady state is valid either in this section or in this section. Okay, so that's very important. And in both sections, I can say that the local acceleration is 0. Now, let's draw the same section again. And look to the variation of velocity with position. For simplicity, I'm going to pick a window here for the velocity meter. So I have specific mass flow rate coming in. Remember, the mass flow rate is function of the flow area, right? And the velocity, right? So if you increase the flow area, your velocity goes down. If you shrink the flow area, velocity goes down to keep the mass conservation concept is valid. So in this situation here, I have a specific location. I selected location and recorded the velocity for a given particle. Let's put that particle in the pink color here. Then that pink particle or the purple particle will continue to move. So the particle will be in here. I will move my velocity meter with that particle and keep my eyes on the velocity. Then after time goes on, it's going to be here, it's going to be here, it's going to be here. Again, I will move my velocity meter with that specific particle. What I'm trying to figure out now is how the velocity would change with location. I'm going to call that location 1, 2, 3, 4, 5. So I picked up 5 locations, focus on the same particle and recording the velocity. So what happened between 1 and 2? So there is a given velocity at 1, the particle moved to position 2. The mass flow rate is still conserved, so the mass flow is not going to change. The pipe diameter is still the same. So I'm expecting that velocity V1 and velocity V2 is still the same. So the velocity did not change with position. Then when I move to position 3, the cross section of the pipe start to shrink a little bit. So I'm expecting the velocity of the same particle at that position 3 will start to increase a little bit. So I would have V3 mainly partially bigger, larger in magnitude than V1 or V2, right? So V3 will be higher in magnitude compared to V1 and V2. So now velocity change it from position 1, 2 to the position 3. What happened when I go for position 4? When I go for position 4, the cross-section area reduced again. So I'm expecting another increase in the velocity. So the velocity would change between 3 and 4. And when I go for 5, I get the final or the smallest flow diameter. So I'm expecting the velocity will reach a new higher level value. So what's happening is the velocity remain constant between 1 and 2. Then when it goes to 3, it will increase. For 4, it will increase. For 5, it will increase. If I mark the same particle at a little bit of down position here, and I record the velocity, let's call that position 6. I'm expecting V5 and V6 will be the same since there is no change in the cross section, the flow cross section area. So the story here is the velocity did not change with position between 1 and 2. So V3 is getting higher here, just to keep writing things, and V4 will go up. V5 will go up, but V5 will equal to V6, right? So it's gonna remain constant. So constant velocity with position, changing velocity, then it's constant again. So I can actually say that I'm ending up here at that location here, that zone 1, that zone 2. So in zone 1, velocity was constant with position. While in zone 2, velocity is not constant with the position. And if I go for zone 3, I'm back, that velocity again constant with position. The magnitude is totally different from one zone to the other, but within the zone itself, the velocity may change or constant. We call the flow that does not change velocity with position uniform flow. So in zone 1, I have uniform flow. In zone 2, I have non-uniform flow. And in zone 3, I am back to uniform flow. So now, if I look the combination of the two cases here, zone 1, so that's zone 2, that's zone 3. So between these two situations here, zone 1 has fixed velocity at a given position with time, and also for a specific position, the velocity does not change from that location to the other. So velocity remain constant at a given position with time, and like this one here, so the velocity here is constant with time, but also this particle, when it moves, it didn't change velocity with position. So in zone 1, we have steady, uniform flow. Steady, because the velocity does not change with time at a given position, and it's uniform because the same particle moved from one position to the other, kept the same velocity. Okay, while in zone 2, the velocity at given position does not change with time. So I'm still steady. But from one position to the other, the velocity changes. So I have steady, non-uniform flow. When you go back to zone 3, if you pick up any particle in zone 3, you put that velocity meter at a fixed position, change the time, velocity is not going to change. It is the same mass rate, same flow area, nothing is expected to change. So the flow is steady, but also because of that uniform cross-section, the motion of the particle from one location to the other is not going to change the velocity. So in zone 3, I'm back to steady, uniform flow. What happened if I picked any particle in zone 1, which is steady uniform, and I start changing the mass flow rate with time? When you do that at a given position, the velocity will change with time. So you become unsteady, but the same particle will continue with the same velocity at the same coil, at the same pipe diameter, so the flow remains uniform. So again, I hope you guys understand the concept now. You pick a location, you track the velocity with time. If it's not changing, that's steady flow, which means that your local acceleration is 0. If the flow does not change from one position to the other, that's uniform flow, right? So that convective term is not going to be exist, right? It's no change relative to the position X, Y, and Z. So this term will vanish, right? For uniform flow, right? This term goes away for uniform. This term goes away for the steady. So if in zone 1 you have a steady uniform, this means that there is no acceleration at all. Steady will cause the local acceleration to vanish, and the uniform will cause the convective or advective acceleration to vanish. When you go for zone number 2, you still have steady, so that term is 0, right? But it's still non-uniform, which means that there is acceleration. The fluid will accelerate, and that's obvious. It's going to change the velocity, but not because of the time effect. It's because of the position effect, because of the particles moving from one location to the other. So I should expect to have a convective or advective acceleration into that zone 2. When I go for zone number 3, I'm back to steady, local acceleration is gone, and I come back to uniform, so the convective or advective acceleration is gone. I hope that explained the difference between the steady flow and uniform flow, and what's the impact of each term into the total acceleration, and how you can understand the combination of having steady or unsteady with uniform or non-uniform flow, depending on the flow geometry.